So this video is going to be an introduction to resonance structures. This is going to be a part one of a two-part video series on how to draw resonance structures, and then some tips and tricks associated with where to start, what to look for, and so forth. So before we get into actual drawings, let's just quickly define resonance structures. So resonance structures are two structures that have the same arrangement of the atoms, but a different placement of electrons. And so at no point should you be moving any atoms within your drawing. The only thing that should be different is how electrons are represented. A few things to keep in mind is that resonance structures are not real. They're just different representations of the possible states that electrons can be found in within a structure. And so the real structure is some hybrid of all of those resonance structures. And those resonance structures can provide information on the reactivity of parts of the molecule, which will be important for us in a couple weeks. Another thing is that resonance structures are not in equilibrium. And so we don't use equilibrium arrows or one-directional arrows to represent those resonance structures. And instead, we use a double-sided arrow instead, which will look something like this. I'll circle it in green here so you can see it. And then the last tidbit for just a definition is that, similar to what I said earlier, resonance structures differ in the placement of electrons. And so primarily what we're going to focus on is going to be the placement of double bonds or triple bonds, and then lone pairs. And so if you're not sure where to start with a resonance structure, always look for double bonds and lone pairs. All right, so let's start off with a simple carbonyl structure. So we're going to just draw a very simple structure here and look at the potential resonance that this molecule could have. And so to show the flow of electrons or difference in electrons, I'm going to use arrow pushing. And so to illustrate the movement from one resonance to another, what we can do is show the movement of these two electrons within this double bond, jumping up to that oxygen. And so we end up with this state where this oxygen started off with 2 lone pairs, and it now has 3 lone pairs. And so based off of this skeletal structure, we can identify the new charges that appeared in this molecule. So if you rewatch the video that I have on skeletal structures, we could calculate that the formal charge on this oxygen right here is going to be -1. And then this carbon down here is going to have a +1 charge. And so to illustrate this, again, we started with the double bond. The arrow starts at the double bond, and it ends where that lone pair ended up. And so I'm going to highlight the double bond in red, and then the lone pair and the oxygen in red as well, to kind of show where each of those electrons ended up. All right, so these are the two structures. We can also draw a resonance hybrid. And to draw a resonance hybrid, what we do is we draw the normal structure that we initially had, and then we use a dotted line to represent any double bonds that are found in only part of the structure. So here, we only see a double bond in this left one, but not in this right one. So we're going to illustrate that by using these dotted lines in the resonance hybrid structure. And then from here, the last thing we have to do is add in the partial charges. So in this state right here, we can see that the oxygen has a negative charge. And so it's going to have a delta minus in the hybrid. And then the carbon below it is going to have a delta positive because it has a positive charge in one of the structures. One thing I want to point out is that a very common mistake I see students make is forgetting to check the charges of carbons. So if we were to think about the hydrogens that are found on the structure, this carbon right here, the one that I just highlighted in green, does not have any hydrogens because it already has 4 bonds right here. And so when it loses that bond to go to this state right here, that carbon still doesn't have a hydrogen because these are resonance structures. We're not adding any atoms, we're not subtracting any atoms. And so the reason it ends up with that positive charge is because it only has 3 bonds, which results in that positive charge. But again, keeping track of hydrogens can be very crucial to making sure you avoid some common mistakes. All right, let's do another practice problem. So here what we're going to work with is starting with a structure that has a positive charge already. And so a pretty useful tip is to look for when thinking about like where to start a resonance structure is looking for positive charges. So whenever you see a positive charge, what you can think of is where can electrons shift over to kind of fill that empty space. And so for this, we want to identify all double bonds, lone pairs, and charges. And so a positive charge wants more electrons, a negative charge wants to give away electrons. And so here we have this positive charge right here. And so we can think about where can we get additional electrons to kind of fill that space. And so for that, we see that we have a double bond on the left over here. And so what we can do is shift those electrons over to form a new double bond between those carbons. And so now we provided that carbon that initially had a positive charge with a double bond. So now it has its complete octet. However, one thing that we'll notice is that this carbon that I just highlighted in green started off with just, I'll draw in the hydrogen too. So if we draw in the hydrogen that was here, still here, what we can see is that green carbon initially had 4 complete bonds, so it was satisfied. However, on the right structure, it now only has 3 bonds. And so we know that carbon with 3 bonds and 0 lone pairs ends up with a positive charge here. And so in our structure on the right, we should draw in that positive charge. And so if we were to draw in the resonance hybrid, what we can do next is, again, we're going to draw out the base structure, and then we're going to draw a dotted line anywhere where we had a double bond at any point of the structures. And so this represents that it's like a partial double bond character. And then lastly, we want to add in those deltas. So we're going to add in a delta positive to both of the carbons that had a positive charge at some point within the resonance structures. All right, so the next example that I want to do is one where we have a negative charge. And so I will draw out this structure here. And so whenever we're starting off a resonance structure and we see a negative charge, what we should be thinking about is how do we get rid of that negative charge and where can those electrons go? And so usually in resonance structures that have a negative charge, usually the first arrow will start at that negative charge. So let's draw in our electrons here on the oxygen. And so here we can start at the lone pair and move down the electrons to form a carbon-oxygen bond here. And so if we were to stop here with our resonance structure, this is the structure that we would get. And so we can see that this is a problem because this carbon right here would end up having 5 bonds. And so we know that we can't have 5 bonds to a carbon, So we cannot stop here with our resonance structure. And so if we go back to our starting state on the left, we have to figure out what to do with that double bond that's down here. And so for this, if we can bump up those electrons to this carbon right here. And so our final state ends up looking something like this, where we have that electrons bump up to this carbon right here. And so this would end up in an overall negative charge on that carbon that has that lone pair of electrons. And so all together, we can draw in a resonance hybrid. To illustrate the kind of, I like to think of it as like almost like an average state. And we have a minus, delta minus on the oxygen and a delta minus on the carbon. And so here, this is just like kind of like an introduction to three different types of situations you might encounter. The first is where you have a neutral molecule, but there's a double bond that can shift. Um, the middle one is one where you have a carbocation and you're looking at how double bonds can rear or shift over to spread out that positive charge across different carbons. And then that last one's a situation which you have a negative charge and you're looking for how you can distribute that negative charge throughout the molecule. And so here I want to take a moment to just draw out some tips and tricks or write out some tips and tricks. And these are addressing some of the most common errors that I see students make. The first is that draw in all hydrogens that are relevant. So that can help you avoid making mistakes when it comes to charges that molecules have, making sure that you're keeping track of carbons that are cannot be a part of a resonance system. The second tip I have is identify all double bonds, lone pairs, and charges. And this can guide you towards like where you should start with drawing the resonance structure. The next tip I have is identify all sp3 hybridized carbons, or in other words, carbons that have 4 sigma bonds. And for these, do not touch these. So at no point should you be moving around anything related to a carbon with 4 bonds. So let's draw this out here. So let's say we have this structure here. And then we take a look at this carbon right here. So based off the skeletal structure, since that carbon doesn't have any charges, we know that that carbon wants to have 4 bonds. So we have to add in those hydrogens. And so now this carbon right here has 4 single bonds or sigma. And so it cannot participate in any resonance. And that's because if we were to shift electrons towards it, then we would get something like this. Let's say that we try to move over that double bond here. And then we would end up with having 5 bonds to this carbon. So we cannot do that because we end up with 5 bonds. And we know that 5 bonds would exceed the octet that a carbon had to have. We also can't shift away electrons from that carbon because if we were to, let's say that we would move these electrons in a carbon-hydrogen bond, then we would end up breaking that bond, and then we would no longer have a resonance structure because those atoms would not be connected in the same like 3D arrangement. Yeah, so in general, first thing I would suggest doing is identifying all those, or one of the first things I recommend doing is identifying all those sp3 hybridized carbons, and then just do not touch them for any of the structures. Do not add bonds, do not take away bonds from that carbon. All right, the fourth tip I have is arrows should always start at a double bond or lone pair. So arrows are always drawn from where the electrons started to where they ended up. So they should always start at where you have electrons, which could either be in a double bond or it could be a lone pair. And then it should never be starting from a positive charge because you don't have electrons there. That's why it's positive. So an arrow should never ever start from a positive charge on a molecule. All right, let's do a few more quick practice questions, and then in part two, I'll have some more detailed and some more advanced practice problems. And here, I kind of recommend maybe pausing this and thinking it through if you want to just get some practice on your own, and then resuming the video once you're ready to go through it. All right, so let's look at the structure here. So as we talked about in these tips and tricks, we're going to first identify where there's possible resonance that can happen, which is going to be where you have any double bond or any charge, which is going to be this part of the molecule here. And then the next thing I want to do is make sure that I'm not touching any carbons that are sp3 hybridized. So this carbon and this carbon right here would both have 4 bonds already, 4 single bonds. So we do not touch either of those. And so going back to the red area, what we can do is shift this double bond over, 1 over, to make a new double bond there. And so that double bond moved over to fill the empty spot on that carbon with a positive charge. And so from here, we have to make sure that we keep track of our charges. So this top carbon right here lost a bond. And so now it only has 3 bonds. And so now we will have a partial or a positive charge on this top carbon right here. And again, we didn't have a hydrogen there in the first place, so we don't have one now. And then to draw the resonance hybrid, we'll do the same thing as before. We'll draw a dotted line through where we had double bonds in the structure. And then we're going to have a partial positive charge on the 2 carbons that had individual charges throughout any of the resonance structures. And one thing I want to point out is that we can see that the total charge on all of these structures is the same as it was initially. So here on this left structure, we had a +1 charge because we had this positive charge here. And then on this other one, we also have a +1 charge here as well. And so every single resonance structure should have a total net charge that's going to be equal across all the states, because otherwise that means we were adding or subtracting electrons when we shouldn't have them. So I'm actually going to add that as a tip and trick to the notes up here. And so this doesn't mean that the charges necessarily need to be the same. So in this example, we have a +1 and a +1. But if we look back to this example up here, in this state, we had no charges, so it was 0. And then in this state on the right, we had a negative charge and a positive charge, which canceled out to be net 0. And so the net charge for both of these was still 0. And so an easy way to just double check any sorts of resonance structures is just to make sure that you have the same total net charge, to make sure you didn't accidentally forget a charge. All right, let's do another practice question. And then in the next video, we'll do more of the, so we'll look at some examples with nitrogens and oxygens. All right. So this one's a little bit more complicated. There's kind of more going on. We have multiple double bonds. And so let's take a look at our system that has double bonds or lone pairs. And so here we have 2 double bonds and then the lone pairs on the oxygen. And so from here, it's not immediately obvious where we can start. One place that we could start is looking at this carbonyl structure right here, the carbon-oxygen double bond. Whenever we see a carbon-oxygen double bond, one potential place to start a resonance structure is to move a pair of electrons from the double bond up to the oxygen. So we can start off the structure by doing exactly that, where we end up with 3 lone pairs on the oxygen because one of the double bonds, now highlighted in blue, ended up here. And then we have a negative charge on that oxygen because now the oxygen has 3 lone pairs and only 1 bond. And so what we'll note is that we initially started off with a +0 or for overall charge. And so if we only do this negative charge on this oxygen, we now have a -1 charge. And so these don't match. And so we know that we're missing a charge here. And so to figure out where we're missing that charge, we look at the carbon that we started off with, and we see that this carbon only has 3 single bonds. And so because it only has 3 single bonds, we'll add in a positive charge. And so this motif right here, the part that I boxed, whenever you see a carbon-oxygen double bond, this is what you should be thinking about. All right, and so now that we have a positive and negative, those cancel out and we match that +0 charge that we initially had. All right, so from here, we can also draw actually an additional resonance structure. And so for this, we can take a look at this double bond right here and this positive charge right here. And so together, what we can do with those is we can shift over this electron density, one double bond shifted over to give that partial positive or that positive charge some electrons. And so we don't touch that oxygen, and instead we just move over that double bond. And so now this carbon right here has its 4 bonds, so we don't have a charge on it anymore. However, this carbon on the end only has 3 bonds, this purple one, because it only has 1 hydrogen attached to it. And so as a result of that, we end up with a positive charge on this carbon right here. All right, so from here we can draw in that final resonance hybrid for the structure. Which will look something like this. where we draw in that skeletal structure first, and then we add in the dashed lines to represent everywhere where we had a double bond, which is across that entire system. And then from here, we can add in those charges. So that oxygen has a partial negative charge. This carbon right here has a partial positive charge, and this carbon on the end also has a partial positive charge. And we're just matching any sort of charges that we saw in the resin structure. So this one comes from this positive charge right here. All right, so I think that wraps up the part one of this video. Again, in the next one, we'll kind of take a look at some more complicated structures and how to approach more advanced resin structures.